Welcome to the 18th lecture in Abstract Algebra. The topics that we'll explore in this lecture include a continuation of our study of cyclic groups. We'll look at groups generated by finite sets, and we'll look at Cayley digraphs and subgroup diagrams.
Okay, so we'll start with the first exercise from the previous lecture, and we'll state this as a theorem. Let G be a group. Then the center of G is equal to G if and only if the group G is abelian. So proof. Suppose that the center of G, which is the set of all those elements in the group G, such that G times A times G inverse is equal to A for every element A in the group. If this is equal to the entire group, then we have that for every pair of elements, G and A in the group, G times A times G inverse is equal to A. That is, for every pair of elements, G and A in the group, G times A is the same as A times G. And hence, the group G is abelian. Conversely, suppose that the group G is abelian, then the center of G, which is the centralizer of the group in itself, is the entire group G, since for every non-empty subset of an abelian group, the centralizer of that subset is the entire group. So the second exercise we will also state as a theorem. Let G be a group and let A be a non-empty subset of the group. Then the centralizer of A is a subgroup of the normalizer of A, which is a subgroup of the group G. So proof. Now recall that the normalizer of A in the group G is the set of all those elements in the group such that the set of conjugations of the elements in the set A by the element G is equal to the set A. Now this set, the set of conjugations of the elements of A by G, is the set of all products G times A times G inverse, where A is an element in the set A. That is, we take the elements of A and multiply each of those elements on the left by G and then on the right by G inverse. So notice that the set of conjugations of the elements in A by the identity is the set identity times A times identity, where A is an element in the set A, and this is equal to the set A, and hence the identity is in the normalizer of A, which is a subset of the group G. In other words, the normalizer is a non-empty subset of the group G. Now let X and Y be two elements in the normalizer. Then the set of conjugations of the elements in the set A by X is equal to A, and the set of conjugations of the elements in the set A by Y is equal to A. Now we can take this set, the set of conjugations of the elements in the set A by Y, and multiply each of those elements on the left by y inverse, and on the right by y, so that you have the set of all products y inverse times y times a times y inverse times y, where a is an element in the set A, and this is the set of all products identity times identity, where a is an element in the set A, and this once again is the set A. And so the set of conjugations of the elements in the set A by y inverse is equal to A. And so we can replace the set A in this equation with the set of conjugations of the set A by the element y inverse. And hence, multiplying the elements in the set of conjugations of the elements in A by y inverse on the left by x and on the right by x inverse is equal to A. This is the same as multiplying all the elements in the set A on the left by x times y inverse and on the right by y times x inverse. Now notice that y times x inverse is the inverse of x times y inverse. And hence the product x times y inverse is an element in the normalizer of A, and thus the normalizer of A in G is a subgroup of G. Now, since it is always true that the centralizer of the set A is a subset of the normalizer of the non-empty set A, and the centralizer of A in the group G is a subgroup of G, we have that the centralizer of A is a subset of the group, which is the normalizer of A and G, which is itself a group under the same operation as in the normalizer of A and G. And so the centralizer of A and G is a subgroup of the normalizer of the set A and G, which is itself a subgroup of the group G. Okay, so as an exercise, prove that the set of conjugations of the elements in a set A by an element X is equal to the set A if and only if the set obtained by multiplying all the elements in the set A on the left by the element X is equal to the set obtained by multiplying all of the elements in the set A on the right by the element X. Okay, so the third exercise from the previous lecture we will also state as a theorem. Let G be an abelian group and let A be a non-empty subset of the group. Then the centralizer of A and G is the same as the normalizer of A and G, which is the entire group G. So proof. Let G be an element in the normalizer of A and G. Then the set of conjugations of the elements in the set A by G is equal to A. And so for every element A in the set A, we have that the product G times A times G inverse is an element in the set A. And hence for every element A in the set A, there exists an element B in the set A such that G times A times G inverse is equal to B. Now, since the group G is abelian, and these are all elements in the group, we can reorder the product on the left so that we have G times G inverse times A is equal to B, or more simply, A is equal to B. And that is, for every element A in the set A, the product G times G inverse is equal to A, and hence the element G is in the centralizer of A and G. And since it is true that for an element, given an element in the normalizer, this implies that that element is in the centralizer. We have that the normalizer of A and G is a subset of the centralizer of A and G. Now, since it is always true that the centralizer is a subset of the normalizer, we have set inclusion in both directions so that the centralizer of A in G is equal to the normalizer of A in G. Now, since G is an abelian group and A is a non-empty subset of an abelian group, the centralizer of that non-empty subset is the entire group, and hence the centralizer of A and G is the same as the normalizer of A and G, which is the entire group. Okay, so new theorem. We will prove that every subgroup of a cyclic group is cyclic. So proof. Let G be the cyclic group generated by some element A, and let H be a subgroup of G. Now, if the subgroup H is the trivial subgroup, that is the subgroup consisting of the identity alone, then this group is generated by the identity, and so is cyclic. Otherwise, there exists a non-zero integer n such that A to the power of n is an element in the set H. Now, as H is a group, given that this element is in the group, its inverse is also in the group, and so A to the power of negative n, which is the inverse of A to the power of n, is an element in the set H. And hence, A to the power of the absolute value of n is an element in the set H, where the absolute value of n is a positive integer. That is, given that H is a subgroup of the cyclic group G generated by the element A, there exists a positive integer for which A to the power of that positive integer is an element in the set H. So, let M be the smallest positive integer such that A to the power of M is an element in the set H. Then the cyclic subgroup generated by this element is a subgroup of the group H. And so a to the power of m to the power of q is an element in H for every integer q. Now we will show that this subgroup H is in fact equal to the cyclic subgroup generated by the element a to the power of m. So let H be an element in the subgroup H of G. Then, as H is a subgroup of the cyclic group G, we have that this element H is equal to a to the power of n for some integer n. Now, by the division algorithm, n is equal to m times some integer q plus r, where r is a non-negative integer that is strictly less than m and possibly equal to 0. And so a to the power of n is equal to a to the power of m times q plus r, which is a to the power of m times q times a to the power of r. And this is a to the power of m to the power of q times a to the power of r. And hence, a to the power of r is a to the power of n times the inverse of this element, which is a to the power of m to the power of negative q. Now, since a to the power of n and a to the power of m to the power of negative q are both elements in the set H, their product, which is a to the power of r, is also in the set H, as H is a group. It's closed under the operation of the group G. And since m is the smallest positive integer, such that a to the power of m is an element in the set H, and r is strictly less than m. This means that r must be equal to 0. And so a to the power of n is equal to a to the power of m times q, which is a to the power of m to the power of q. That is, for every element H in the set H, that element is equal to a to the power of m to the power of q for some integer q. And hence, the subgroup H is the cyclic subgroup generated by this element, and so is cyclic. And so in either case, a subgroup of a cyclic group is cyclic, and therefore every subgroup of a cyclic group is cyclic.
Now this theorem has an interesting corollary.
We can show that the subgroups of the group of integers under addition are precisely the groups of integer multiples of the integers under addition. So proof. The set of integers is generated by the integer 1 and therefore is cyclic. We have demonstrated that the integer multiples of the integers is the cyclic group generated by the integer n, which is a subgroup of the integers, and by the previous theorem. These are the only subgroups possible. And therefore, every subgroup of the integers under addition is the group of integer multiples of the integers by some integer n.